Hello everyone. Uh, Today we will look at another chapter in the basics of aerospace and engineering. Today we are going to look at what is something called as an ornithopter. Okay, and ornithopter in layman terms is the aeroplane or a plane kind, which an aircraft which is looks like a bird. Now, what is ornithopter? An ornithopter is an aircraft that flies by flapping its wings. Designers sought to imitate the flapping wings flight of birds like bats and insects. Though machines may differ in form, they are usually built on the same scale as the flying animals. And this is taken from the Greek word ornis means ornith means bird and pteron means wing. There are different types of ornithopter: the flapping wing ornithopter, fixed wing ornithopter, rotary wing ornithopter, hybrid ornithopter, and the biomimetic ornithopter. It, it's an aircraft heavier than air that flies like a bird by flapping its wings. Is a type of an aircraft that mimics bird flight by flapping its wings to generate both lift and the thrust. The concept was first explored by Otto Lilienthal in 1889 and has since been developed by researchers and has been used in the industry. The operating principle of the flapping wing. It goes like this: ornithopter mimic birds' flight by generating lift and thrust through flapping. During the downstroke, lift distribution is generated and shifted towards the wingtip, resembling a propeller blade generating thrust. Conversely, during the upstroke, lift distribution is smaller and shifted towards a wing root, acting more on a wing turbine blade. Efficiency increases with the addition of fuselage and tail unit, allowing the ornithopter to overcome the parasitic drag and delivery power. These are the forces that come on the wing. The various forces: airflow due to the airplane's forward motion, due to the flapping motion, and the relative flow during the upstroke and the downstroke is been shown here. Influence of the lift distribution: turning and flapping wing around its longitudinal axis affects its lift magnitude but not its distribution along the span, as observed in bird flight dynamics. The maximum lift coefficient happens when the wing turning is limited by the maximum permissible lift coefficient of the aerofoil or airfoil at the wing root, which determines the extent of lift increase achievable. Birds utilize wing turning, particularly during increased thrust requirements, to optimize the lift generation and minimize the negative thrust, enhancing the overall flight efficiency. Now, there is flapping wing properties during the flight. Balance torque, leverage effect, and the thrust lift trade-offs are generally being seen here. Wing twisting during the upstroke can balance torque around the wing hinge, where the inner wing section acts as a wind turbine, while the outer wing section acts as a propeller, resulting in zero net thrust. Positive lift near the fuselage must exceed the negative lift near the wingtip to facilitate upward wing movement without external force, maintaining some positive lift overall. Concentrating lift at the midspan during the upstroke reduces the negative thrust with additional support from downward bending of hand wings, allowing for strong lift without doubling the wing area or causing excessive fluctuations. The seagull in cruise flight is perfected according to the literature, and it shows in particular the two following characteristics: a very slight, sometimes barely observable bend of the hand wing to downwards, and then approximately constant carry force. Thereby, an up and down swinging of the bird is no longer observable. Strong inclined climbing and hovering. Flying with the thrust in flapping wing. Thrust directed either upwards or downward balance the weight during the flapping flight, akin to the helicopter. The energy demand. Flying with thrust demands more energy, particularly in large ornithopter, compared to pure flying with lift. While the bird flight literature often focuses on induced drag during slow flight, the Otto Linenthal recognized the distinction between the power flight types in birds, acknowledging the significant energy demands of slow flight too. We have something called as wing route adjustments, the forearm dynamics, and the flight configurations. Birds adjust lift near the wing route by angling the arm and utilizing the tendons of forward flight skin to increase the width, wing depth. Longer forearms cause the wrist to shift forward when the arm wing is angled, altering the tendon pulling direction and increasing the wing depth near the elbow. Birds configure the arm wing directly differently for various flight modes, adjusting wing depth to stabilize flight and optimize lift distribution. The applications of our ornithopter goes like this. Because the ornithopters can be made to resemble birds or insects, they could be used for military operations such as aerial reconnaissance without without alerting the enemies that they are under a surveillance. Several ornithopters have been flown with video cameras on board, some of which can hover and maneuver in very small spaces. Right. So this is the application of Ornithopter, and we will meet again on another video. Thank you very much for listening.